primary classification example. So in order to do that, we are using cancer classification.csv. And in this particular cancer classification.csv, there are so many features that are available. So here, if you observe, we have mean radius, mean texture, mean perimeter, mean area. Like that, we have so many features, input features. And based on all of these input features, we have our output feature, that is this one. This one will be telling us whether the person is affected with cancer or not. Okay. So 0 means that he is not affected, whereas 1 means that he is affected with cancer. So now let's load this particular data and let's see how we can solve this particular problem. So initially we are reading this particular cancer classification.csv, and after that we are checking how the data is looking like using df.head, and these are all the columns that are available with us. And finally this is our output column that we have, and we can see how our data is looking like, or we can get some information about our data using this df.info. It will be telling us what are the total number of data points that we have, and also what are all the input features that are available with us, and similarly what is the data type of each of these input features. All these details will know from this df.info. And then we are trying to find out whether are there any missing values in this particular columns or not. So in order to find out that, we can simply use this df.isNull.sum, which will be giving the exact number of missing values in each of the columns that we have. But if we carefully observe, like there are no missing values in any of our columns that we can clearly observe from this. So now let's move on to the next one, that is df.describe. And I hope you guys already know what is this df.describe. We have seen this before as well. Basically, for each and every feature that we have, it will be giving some details like mean, standard deviation, minimum value, maximum value, and also 25th percentile, 58th percentile, and 75th percentile. All these values will be calculated and will be shown to us. So if you wanted to find out what is the mean perimeter on the whole data set that we are having, then it is 91.96. Like that, we can know some important information about the features that we have. Okay. So in this way, this particular describe will help us. Let's try to understand a little bit more about the data set that we are having. So in the data set, as I said, we are having some input features, and finally we are having the output column, so which will represent whether the patient is having cancer or not. Okay. So whenever we are having such data, it is really important to know how balanced the data is. Okay. So in order to know that, we can just simply make one count plot on the output feature that we have. So our output feature is this one, and the data that we are having is in this particular data frame. And on doing this, so this is the graph that we are getting, where 0 represents that the people who are not having cancer, and 1 represents the people who are having the cancer. Clearly, some near to 200 people are not having cancer, whereas near to some 350 or 360 people are having cancer. So this is our data distribution that we have. And basically, if we carefully observe over here, there are up to 30 number of features that we have. So total, starting from 0 uh, till 30, it is going on, where this last column is our output column. So there are total 30 input features that we have. So using these 30 input features, we need to predict the output that we are having. So this is the ideal thing that we need to do. But as we discuss some pre-processing techniques, what we can do something like feature selection, and then we can do something like feature engineering, and then followed by removing the missing values, and data encoding, data scaling. All these things we have already discussed in the previous videos. And the first one, as I said, it is feature selection. So according to feature selection, we can see the data, and if we feel some of the features are not important, then we can remove them and reduce the total number of input features that we have. So in order to do that, either if we have knowledge on that particular domain on which the data set is present, then we can do that directly. Or if not, we need to follow some mathematical strategies in order to do that. Okay, so here if you observe, cancer is not very related ourselves, because we don't know much about how cancer affects, or how our output is affected by the input features that we have, that we are not able to understand from the features that we are seeing over here. So what we can do is we can simply choose two features out of these 30 features and make a plot between those two and see how related are the features that we are having. So we can do this for all the features that we are having. So total, if we choose like every possible two features and make some plots and try to understand the relation between them, it will take too much time, because the total number of graphs will be like 30C2, right? Because from 30 features we are trying to choose some two features and trying to plot based on those two features, right? And then extract out the relation or find out the relation between them. And finally, after making several conclusions, we might wanted to remove few of them. So it is too time taking process. That's why simply, in order to do the same, what we can do is we can simply go for using the correlation matrix, which will be giving us some gist about how well related are the input features that we are having, or how well related these input features are with the output that we are having. All these details we can know simply by using this df dot correlation. And if the correlation value is near to +1, or if it is near to -1, that means that they are highly correlated. So if it is near to +1, what does that mean? That means that with the increase in feature 1, the feature 2 is also increasing. Okay, so let's say correlation between feature 1 and feature 2 is almost near to 1, or we can say greater than 0.5. That means that with the increase in feature 1, proportionately feature 2 is also increasing. Okay, and similarly, if it is near to -1, what does that mean? With the increase in feature 1, proportionately feature 2 is reducing. Okay, so this is what this +1 means, and this is what this -1 means. Whether it is +1 or -1, we can say that both the two input features are highly correlated. Okay, if we wanted to find out whether two features are not at all correlated, that we can understand if the value is near to 0. Okay, so I hope you got some clear idea what this correlation value represents. So as there are too many features, we are not able to understand from this particular big heat map as well. So simply what we can do, we can take out some part which is related to our output. So let's simply concentrate on this part only, that is how each feature is correlated with our output that we are having. Okay, so that we can remove some of the features that we have. Okay, so it is not completely necessary to remove features, but in case if you wanted to remove features, then this kind of strategy might work for you. Okay, so simply we are taking the last this particular column in the correlation matrix. That means if you're taking it's like taking this particular column completely, or this particular row completely, and this row we are sorting, and these are the corresponding features and their correlation values with the output that we are having. And if we plot this, so all these are highly correlated because these are near to -1, whereas like near to 0 few of the points were there, and it is not crossing 0.25, whereas the last one is same as the output, that's why it is equal to 1. Okay, so if you wanted to remove any of the features from this, it is better to remove these points which are near to 0 instead of removing these, because these are related, these are highly correlated with the output that we are having. Okay, but these are not at all correlated to the output that we are having. So if you wanted to remove, you can remove, but for now we are not interested in removing any of the features that we have. So simply we are keeping all our input features, and in y we are keeping our output, that is this particular column. And finally we are doing train test split. 25% of the points are in our testing data set, whereas remaining 75% will stay in the training data set. And these are the corresponding train and test shapes. Okay, in training data we are having 426 points, whereas in our testing data we are having 143 points. And after that we are doing some scaling. So using min max scaler, what it will be doing, it will try to make the minimum value to 0, whereas the maximum value to 1. So first we are fitting it on training data, and then we are transforming it on both training and testing data. Okay, and here if you observe, it is 30 because we are having 30 number of input features. Now let's build our neural network that we are having. So what is the first layer? First layer should have input features. And how many number of input features are we having? We are having total 30 number of input features. And then followed by, we are building our neural network. So in the first, this is our first layer, first hidden layer, or the dense layer. Okay, so in the first hidden layer, what is the number of neurons that we are having? We are having 30 number of neurons. So we are having 30 neurons in the first hidden layer. 1, 2, 3, so on till 30. And what about the second hidden layer? In the second hidden layer, we are having 15 neurons. And finally, in the last layer, we are having only one neuron. What does this last layer called as? Last layer is called as output layer. And we already know that if we are trying to solve some binary classification problem, we can simply have one neuron in the output layer, or we can even have two neurons. If we are using two neurons, then what is the activation function that we need to use? We need to use softmax as our activation function. Whereas if we are using only one neuron, then the activation function that we need to use is sigmoid. Okay, so this we have already seen several number of times by now. So here we'll be using sigmoid. Whereas on the hidden layers, what is the activation function that we'll be using? We'll be using relu as our activation function on the hidden layers. So this is our overall neural network structure. Out of this, we'll be getting the predicted output, and all these will get connected like this. Okay. Can anyone tell me what will be the total number of weights in W naught? It will be 30 into 30. Those are the weights on the connections that we have, and plus 30 bias terms will be there, where each bias term will be uh, corresponding to one neuron in this particular dense layer. Okay, like this, the total number of parameters in the W naught will be 30 into 30 plus 30. And similarly, what will be the total number of parameters in W1, or what will the total number of weights? That will be, please comment your answer in the comment section before I say the answer. Pause it and try to comment your answer. So it will be 30 into 15 plus 15. So whereas these 30 into 15 are the weights on these connections, and these 15 are the bias terms for each of these neurons. Okay. So like that, we'll be getting the total number of parameters on this W1. And similarly, between this hidden layer 2 and the output layer, we'll be having W2, and the number of weights in W2 are 15 into 1 plus 1. So this will be the total number of weights that we are having. And in forward propagation, what we'll be doing, we'll be initializing all the weights to some random values, and then we'll be passing our input that we take from the data set that we are having, that is like mean radius, mean perimeter, like all those input feature details will be passing over here. On passing this, it will go through this whole network, and finally we'll be getting the predicted output. Once we get the predicted output, we'll be calculating the loss. And if it is a binary classification problem, what is the loss function that we'll be using? We'll be using binary cross entropy as our loss function. Okay, and we can use some advanced optimizer in order to adjust all these weights. And how the weights will be adjusted? First we'll be adjusting W2 weights, and after adjusting all the W2 weights, then we'll be adjusting W1, and after adjusting all the weights in W1, then we'll be adjusting the W0 weights. So this is the order that we follow, and this order we can call it as back propagation. So all these details we have already seen in the last videos also. So just For binary classification, we need to make main changes in the output layer, the activation function, and also the loss that we are using, that is binary cross entropy. And optimizer, we can use any of the advanced optimizers like Adam. And metrics, we'll be using accuracy. As it is a binary classification problem, we can simply go for accuracy. And then we are fitting our model and we are mentioning the epochs to be 600. And I hope you guys got to know what is the difference between an epoch and an iteration. And then we are passing our validation data as our testing data itself. Okay. This it runs for 600 epochs. And if you check the model.summary, it will be giving the details about the number of parameters in each of these cases. We have written this number, right? You can check it whether we are writing it correctly or not from over here, which will give us how good we understood about the model. That information we'll know. We can know by manually calculating these and matching with this particular model.summary. Okay. And these are all the information that we get from this particular model.history.history. That means this loss, accuracy, validation loss, and validation accuracy were saved in this model.history.history. And using this loss and validation loss, if we plot what is happening, our loss and validation loss are reducing till some point, but after some point, this particular validation losses keep on increasing, whereas this particular like training loss is slowly reducing. Okay, that means training loss is reducing, whereas validation loss is increasing. Have you guys seen this pattern before in my classes? And if you have seen already, so what does this pattern represent? Or what is happening to the model? Can anyone comment down in the comment section? Maybe in the next video, we'll be discussing what is the problem with this model and how to resolve such issues if you are having any. All these details we'll be discussing in the next video. Okay. So I hope this video is clear for everyone. And if you have any doubts, please comment down in the comment section. Thank you everyone. Bye bye.